In this last lecture of chapter 18, we'll look at three sample problems, two involving ideal gas law and one involving thermal expansion. All right, so in the first problem, we have a situation that we have a lake which is 50 meters deep, and there's a little air bubble that rises from the bottom of the lake to the top of the lake. Now, when it's at the bottom, the temperature, the surrounding water temperature is 4 degrees Celsius. Why 4 degrees Celsius? Well, we explained before in thermal expansion, and this is where the density of the water is highest. So water at this temperature tends to sink to the bottom of the lake, right? And then this bubble rises all the way to the top of the lake, and this is where it will expand. Why does it expand? Well, there are a couple of things. One is that the pressure in the bubble will be smaller due to the decrease in the surrounding pressure of the water. And secondly, it's also because the temperature at the top of the lake is higher than that at the bottom. So in both cases, you can see an increase in the size of the bubble. So suppose the initial radius of the bubble is 3 millimeters when it's at the bottom of the lake. What we want to know is what is the radius when it rises to the top of the lake. Right? Now, treat the air trapped in this bubble as an ideal gas, which will be an excellent approximation. What we can do is we're going to apply the ideal gas law to the two states, one at the bottom of the lake, the other at the top of the lake. The quantity of the air inside did not change. Okay, so we can apply P V over T equals a constant. That constant equals the number of moles trapped inside times the ideal, the universal gas constant, and both are constants. They both did not change. So if I call one state the initial state, right? Let me call this the initial state, and this the final state. Then I have from the ideal gas law, I have P initial, V initial over T initial equals to P final, V final over T final. Okay, now let's look at the initial pressure. Okay, that's the pressure of the surrounding water at the bottom of the lake. It's 50 meters deep, so the water produces its own pressure due to its weight. But don't forget, there is also the air pressure pushing the water down from the top of the lake. That's 1 atm. I'm assuming, of course, normal circumstances, 1 atm. Or you can say 1.01 times 10 to the 5 Pascal, if you use Pascal. Now, we can use either Pascal or ATM, but in this case, probably easier to use ATM because we know that at the top, it's 1 ATM going down. And also we know that with every 10.3 meters of increase in depth, the water pressure rises by 1 atm, right? So here we have 50 meters, right? So 50 meters. So we have, so what is the pressure at the bottom? So the pressure at the bottom was P initial equals what? P naught, which is 1 atm plus rho water G times H. And we know P naught is 1 atm, right? Plus the next term is the pressure due to the depth of the water. And we know for every 10.3 meters of increase in depth, it rises, the water pressure rises by 1 atm. So it's going to be 50 divided by 10.3 meters times 1 atm. Okay, this is a little bit easier to calculate numerically than using Pascal. So if you do that, you can find the pressure at the bottom. It's pretty close to 6 atm, but not exactly. Let's do a little calculation here. 50 divided by 10.3. That is 4.85 plus 1 atm at the top. It's 5.85. Okay, so that's the pressure at the bottom. The volume at the bottom, I only know the radius, but the volume is proportional to the radius, R initial or R naught. Why don't we just call it R initial? R initial to the power 3 And also we know V final is proportional to R final to the power 3 as well. It's a circular, it's a spherical bubble, we assume. Okay, now, so that's P, that's V. In fact, I have to also find P final. P final is at the top, that's 1.0 ATM, right? And then T initial and T final. T initial is when it's at the bottom, it's 4 degrees Celsius. So in Kelvin, we have to convert to Kelvin. In the PV over T was a constant expression. T is given in Kelvin, so it's never negative and never 0. Okay, 273, and that is 277 Kelvin. Okay. Now at the top, T final is 20 degrees Celsius. So 20 plus 273, that'll give you 293. All right. So we got all these numbers in place. So we plug all these numbers back into the formula at the top, the ideal gas law, and let's see what we come up with. We have P initial. First of all, let me rewrite. Let me rewrite this a little bit. Okay. Let me solve for. Let me plug in V initial proportional to R initial to the power 3, and V final proportional R to the final power 3, and then I have P initial R initial to the power 3 over T initial equals P final, R final to the power 3, and then T final. Okay, let's do that first. And then I have R final over R initial equals what? You can solve for that. It is going to be T final over T initial, and then P initial over P final. Everything raised to the power 1 over 3. Right? So let's plug in the numbers now. It is T final 293 times P final, P initial, which is 5.85 ATM. Okay, I'm using ATM for both P initial and P final, so the units nicely cancel out. And then you have T initial, which is 277, and P final, which is 1.0 ATM. Okay, everything raised to the power 1/3, and you can solve for V final. Okay, so R final equals R initial times this factor. Okay, equals R initial times this factor. You know, whatever factor that you just got. Just calculated, power 1/3, right? And R initial is 3 millimeters, right? Is 3 millimeters, and you do this calculation, millimeters times this factor, and you can finish your numerical calculation, and the answer you get is 1.85 R1 or R initial, and that is 5.6 millimeters. Okay, 5.6 millimeters. So the size of this bubble increased, the radius increased by a factor of 1.85 to 5.6 millimeters. So basically, we just applied the ideal gas law to this bubble, considered its temperature change and its pressure change, which will bring in a volume change, which results in the change in its radius. Right. So this is the case with ideal this bubble, which is an ideal gas, did not change any mass. Okay, there's no leak or anything, so we can just use P B over T equals the same constant for these two states. Okay. Now the next problem is a little bit more interesting. We have a situation where we have an oxygen tank. Okay, an oxygen tank with a certain volume, certain pressure, certain temperature in the initial state. Now, suppose we use up some oxygen. Okay, we lost 100 grams of oxygen and use it up. We end up with less oxygen trapped in the same tank, so it's got the same volume. The temperature has also decreased a little bit. What I want to know is what is the final pressure? Okay, so in this case, you got to be careful because the number of moles changed from initial to final state. So you cannot use PV over T equal to the same constant for these two states because N, the number of moles, has changed. So how do we do this problem? Well, we can write down the ideal gas law for the first or initial state, and we also write it for the final state, and we go from there. So for initial state, I have P initial, V initial over T initial equals to N initial R. Be careful, I did not use just a generic N, I used N initial because N final is going to be different from N initial. N initial is the number of moles of the oxygen before 100 grams of oxygen got leaked out. Okay, and then similarly, I can find for the final state, I have P final, V final over T final equals N final R. Now I know T final, 5 degrees Celsius, you can convert to Kelvin. I know V final, this is actually V final. Okay, V final is the same as V initial. In order to find P final, all I need to do is find N final. Right? If I know N final, I can go ahead and solve for P final. Now, N final is not equal to N initial, right? It's not equal to N initial. It is in fact equal to N initial minus delta N. Delta N is the amount of mole of oxygen lost when you release 100 grams of oxygen. Okay. Now, what you need to do is to find an initial and delta N, and then you can go ahead and solve for P final, right? What is N initial equal to? Well, that's given in this expression right here, in this expression, right? Because we can solve for N initial. So what is N initial equal to? So N initial equals to P initial, V initial over R T initial, right? I know what P initial is, V initial R, I know everything. So numerically, we can find what that is. P is given in this case in ATM, so you can convert to Pascal if you want to, but we can keep it in ATM for now. ATM, okay, ATM. V is 20.0 liters. You notice I've written down the units explicitly. Usually I don't do that in the middle of the calculation, but this is something I want to do here because this R has different choice of units. I'm going to choose the units to cancel with ATM and L. Okay, so R, there are different values of R. You can use the standard value of 8.31, but that's in in the SI unit like joule and Kelvin and and mole, that sort of thing. But here we have to use ATM and so on. So the value is a little different, right? So the value we're going to use in terms of ATM and liters, as you know, we saw that in a previous lecture, it is equal to 0.0821 ATM liter over Kelvin. So you see ATM liter nicely cancel out numerator denominator. And then T initial is 20 degrees Celsius. You add 273 to convert to Kelvin, that's 293 Kelvin, right? So Kelvin and Kelvin cancels, liter and liter cancels, ATM cancels, you just get moles, right? You just get moles. Actually, there's a mole here in the unit, in the denominator here, in R. So that will give you N initial in moles. You plug in on numbers, the answer you get would be 12.3 moles. That's the number of moles of oxygen before you lose 100 grams. But what's delta N then? Delta N is the amount of moles of the oxygen gas left. Okay, that has escaped, and that's 100 grams. Now, if we know the molar mass of oxygen which is 32 grams per mole, then 100 moles corresponds to a certain number of moles. So delta N, you can easily find that with 100 grams divided by the number of grams per mole, which for oxygen, O2 is 32, right? Grams per mole. And if you do that, you find delta N to be 3.13 mole. So you start with 12.3 moles and you lost 3.13 mole. So therefore, N initial minus delta N would be equal to 12.3 minus 3.13, and approximately that would be 9.3 or 9.2 moles. Okay, that's N final. Now, then what you can do then is to use the ideal gas law after for the final state, which is this guy right here, okay? And you can solve for P final or P final rather. So let's do that. Okay, so you now have P final equals what? Equals to N final or T final over V final. Okay, and N final, as you know, is about 9.2 moles. Okay, moles, but this time, depending on what the units I use for the volume and for the pressure, I can again choose R to be either 8.31, that's the standard joule mole Kelvin, or I can use 0.021 for ATM and so on. And since the initial pressure is given in ATM and the volume is given in liters, I'm still going to use that 0.0821 ATM L liters over mole Kelvin. I can still use that. And T final is 5 degrees Celsius. You add to 73, you get to 78 Kelvin. Okay, you got to convert to Kelvin. Don't forget for the temperature. V final is the same as V initial, it's 20 liters. Okay, 20.0 liters. And if you do this calculation, it's going to get you the final. It's going to get you the final pressure, and that equals to 0.75 of the initial pressure. Okay. So it turns out to be 0.75 of the initial pressure. The initial pressure is 15 atm. So you're looking at about 11.3 atm. Okay, that's the final answer. So in this second sample problem, we look at ideal gas law again. But the interesting part of this problem is that we're looking at a case where the mass or the number of moles of this ideal gas has changed. So you cannot equate PD over T for initial final state directly. You have to apply the ideal gas law separately to both states. Okay, so that's the second sample problem. Now the last sample problem involves thermal expansion. It's actually a combination of thermal expansion and compression, or Young's modulus. You remember Young's modulus? We learned in physics 8A, right? When you stretch or compress a material linearly, you're going to get a change in its linear size, right? Stress versus strain, right? So we have a situation like this. We have a rod of length L and cross-sectional area A trapped in between two rigid walls. That's a distance L apart. So this wall here, this wall here and this wall here, they are both rigid and immovable, and the distance between them is always L, no matter what. All right, now there's a rod that's trapped in between. Right now, at a certain temperature, this rod is under no tension. There's no stress pushing on it, okay? Because the rod has the length L, which matches the distance between the two solid walls. Okay, so it's not being compressed nor stretched. What happens though, if I give it a temperature change of delta T? Well, if there is no such pair of walls impeding the expansion of the rod, then the rod is going to expand by how much? Well, we know delta L would be equal to alpha L delta T, right? Okay, so it's going to expand by this much, and still there's no tension. Both ends are free to move. But the problem here is that there is actually a pair of walls, so the length cannot change. So imagine you expand this by delta L due to thermal expansion, but the wall compresses you back, right? So you end up having reached the same old length because of a compression. So how much does it have to compress? It has to compress back by the same amount, don't you think? Right? You expanded this thermally, and then the walls will allow you to, will push you back to the same length, so you end up getting compressed by this amount, right? So the question now is, under this kind of compression, how much stress is there in the wall? This has to go, we have to go back to the definition of Young's modulus. As you know, the Young's modulus says Y equals to stress over strain. Okay. You learned that in physics 8A. Now, stress is delta L over L. Actually, that's strain. Okay, stress is the amount of force applied per unit area. Okay, the amount of force F applied to the rod per unit area. The cross-section area of the rod is A, that's given. Strain is the percent change in its length, that's delta L over L. Okay, what I'm looking for? I'm looking for the amount of force the wall has to exert, the walls have to exert to keep the rod under the same length despite the temperature change. Okay, so now we can solve for F. So F would be equal to Y times delta L over L, right? Y times, and then times A, right? And again, we know what delta L is. Delta L is alpha L delta T. So Y times alpha L delta T, then divided by L, that's alpha delta T. And then times A. So this the final expression that we get here gives us the force that the walls will have to provide to push the rod in so that despite the thermal expansion, it will keep the same length. Okay, so this is an interesting problem in which we have to combine our knowledge for both stress and strain and thermal expansion. And this is also a real life engineering situation where you have to consider, what happens when the material is under thermal expansion due to seasonal temperature change, and how much additional stress that will put on, the neighboring structures to keep it in place.